Three sample configuration. The Fano plane. The Fano plane, after genus Fano, is the finite projective plane of order 2. It is the finite projecting plane with the smallest possible number of points and lines, 7 points and 7 lines, with 3 points on every line and 3 lines through every point. This is a model of Fano's geometry. As you can see, there are 7 points, 1, 2, 3, 4, 5, 6, 7, and 6 straight lines and 1 curved line. Now let's proceed with the axioms. First, there exists at least one line in the Fano plane. Number 2, every line of the geometry has exactly 3 points. 3, not all points of the geometry are on the same line. 4, for each 2 distinct points, there exists exactly one line on both of them. 5, each 2 lines have at least 1 point on both of them. Next is, let's proceed with the theorem. Theorem 1. Each 2 distinct lines have exactly 1 point in common. Proof. Suppose 1 and 2 are distinct lines in Fano's geometry. And by axiom 5, it says that there is at least 1 point on both of them. If points P sub 1 and P sub 2 are on both 1 and 2, then axiom 4 is contradicted as there are 2 lines on both P sub 1 and P sub 2. Theorem Fano geometry has exactly 7 points. Proof. We've established that there are at least 7 points. Suppose there is an 8, P sub A. By axiom 4, there must be a line that contains both P sub 1 and P sub 8. Since must intersect the line that contains P sub 3, P sub 7, and P sub 4, and that line contains no other points, it follows that contains either P sub 3, P sub 7, or P sub 4. This contradicts axiom 4. Theorem. Fano's geometry has exactly 7 lines. Proof. Suppose Fano's geometry had a line that was not among the 7 we've established. And by the axiom 4, each 2 distinct points must have exactly 1 line on both of them. Thus, cannot contain at most one of these 7 points. By axiom 2, though it contains 3 points, therefore contains at least 2 points that are not among the original 7. This contradicts our previous argument that there are exactly 7 points in the geometry. Now let's talk about the Pappus configuration. Pappus configuration is a 9 points and 9 lines in the Euclidean plane with 3 points per line and 3 lines through each points. Now let's talk about the Theorem 1, the Theorem of Pappus. If A, B, and C are 3 distinct points on one line, and if A complement, B complement, and C complement are 3 different distinct points on a second line, then the intersection of AC complement and CA complement, AB complement and BA complement and BC complement and CB complement are collinear. This is the picture that I'm talking about. As you can see, if points A, B, and C are on the line, and A complement, B complement, C complement are another line, then the points of intersection of the lines AB complement, AC complement, and CA complement, and BC complement, and CB complement lie on a common line that called the Pappus line. This is the Pappus line, it's the yellow one. Okay, now let's proceed. Number 1. There exists at least one line. 2. Every line has exactly 3 points. 3. Not all points are on the same line. 4. There exists exactly one line through a point not on a line that is parallel to the given line. 5. If P is a point not on a line, there exists exactly one point P complement on the line such that no line joins P and P complement. With the exception in action 5, if P and Q are distinct points, then exactly one line contains both of them. Now let's proceed with the theorem 1. Proof. Theorem 1.10. Each point in the geometry of Pappus lies on exactly 3 lines. Proof. Let X be any point. By corrected axiom 3, there is a line not containing X. This line contains points A, B, C, which tells by axiom 2, X lies on lines meeting 2 of these points, say B and C. By axiom 5, there is exactly one line through X parallel to the BC. There can be no other line through X since by axiom 4 it would have to meet BC at a point other than ABC, or axiom 6 and 5, and this would be contradicted. Now let's talk about the Desagues configuration. It's a configuration of 10 points and 10 lines, with 3 points per line and 3 lines per point. It is named after Gerard Desagues and closely related to Desagues' theorem, which proves the existence of the configuration. Now let's proceed with the axioms. There exists at least one point. 2. Each point has at least one polar. 3. Every line has at most one pole. 2. Two distinct points are on the most line. 5. Every line has exactly 3 distinct points on it. 6. If a line does not contain a point P, then there is a point about the line and any polar of P. Next, this is Desagues' theorem 1. Theorem 1. Two triangles said to be perspective from point if 3 lines joining vertices of the triangles meet at a corresponding common point called the center of a polar point. Theorem 2. Theorem 2. Two triangles are said to be perspective from a line if the 3 points of intersection of corresponding lines align on common line called the axis. Yeah, there's a pictures below, as you can see. And the last, Desagues theorem 3. Two triangles are perspective from a point if and only if they are perspective from a line. And that's all. Thank you for watching.